We're going to talk about applications of the cross product a little more, okay? Finding areas of parallelograms and triangles, that's cool and all, but, it's probably not going to pay the bills. So we want to be able to prepare ourselves for, life. So we're going to take the cross product and do some more useful things with it, like find torque, okay? Torque is basically... If you apply torque to something, you're going to cause it to rotate around a central axis, okay? So if you apply torque to a gear, a wheel, a 8-inch American-made crescent wrench. Hang on here. Yep, it's 8 inches, all right. So we got that out of the way. I'm glad we're all taken care of there. So basically, this is the cross product right here. So if we take the magnitude of the force we apply to it, multiply it by the length of the application, multiply it by the angle we apply the force, we'll get the torque magnitude, okay? And this R vector here, okay? Actually, I might as well just draw the magnitude bars around it. That means length of application. So that's actually one of the reasons they stamp this on here, and these come in sizes, okay? So just offhand, what's going to happen is sine theta goes to 0 here. Our torque's going to go to 0, right? Think about it, dude. If we're pushing all of our torque straight this way, this thing isn't going to move, okay? Likewise, if we push all our torque this way, it's not going to move, it's not going to turn the bolt either. So you'll have the sine of 0 or the sine of 180 degrees. Both are 0. It gives us nothing. Likewise, if we apply our force at right angles, we're going to get the most torque, right? Because sine will be 1. If it's here, sine will be less than 1. That'll kind of modify our answer. It'll take it down a little bit. Same thing here. Same thing here, okay? Well, if we're not careful, see this angle right here, now it's obtuse. Well, now our sine is going to be negative, okay? So it makes sense, I mean, the closer we get to straight up and down and vertical, the more force makes it, to our bolt down here, okay? Now, furthermore, let's just say the angle is constant, okay, and the force is constant. Well, if I use a longer wrench, heck, we know that back from, third grade science, if we, the levers, that'll take everything. So that's just, some kind of intuition behind it, and this is definitely a real world example, because torque is all over the place. I mean, it's everywhere. So, okay, but basically, let's figure out the torque on this wrench right here. So, let's say... Let me get some paper. Let's say that, okay, well, we know that R is equal to 8, so we can go ahead and just write that down. And usually they use a symbol tau. It's kind of like pi with one leg. And how much force am I going to put down on this thing? I'm going to put 20 pounds on it. 20 pounds, okay, and let's see here. What angle am I going to do this at? Let's say I'm pulling. Let's say I'm pulling not quite there. I mean, I'm underneath my car or something like that. I can't reach anything, so I'm going to pull this way. So if I'm pulling this way, I'm applying my force in this direction. It doesn't matter if it's on this side of the wrench. It doesn't matter if it's on this side of the wrench. So if we look right here, this angle is about 40 degrees. I don't want to say 45 because everyone knows the sine of 45 degrees. So let's go sine of 40 degrees. Okay? Well, this is basically, if I push on the wrench right here, this little guy we've did, this is going to tell us how much torque is on the head of that bolt. And of course, we're neglecting things like friction. Maybe, there's usually a little play in a crescent wrench, unless it's American made. So here we go. 8 times 20 times sine of 40. Okay, so you get, call it 103. Okay, now our units are a little different. Okay, let's take a look at our units. Okay, this was measured in inches and this was measured in pounds, so it's going to be in inch pounds. Okay, so 103 inches, okay, times 1 foot is 12 inches. So I'm going to divide my exact figure by 12, and that gives you this about 8.6 foot-pounds, okay, which is equal to 8.6 foot-pounds. Okay, you've heard of foot-pounds probably before. If you're an engineering student, I hope you've heard of foot-pounds before. So that's a real-world application of the dot product, and I really wanted to show you that. And it's a simple one too. It's not that hard. Now let's do a couple. Let's think about a couple other things. You know, could we have found this out? You know, if we didn't know one of these, you know, we could have guessed. You know, we could have done something like that. But yeah, you know, we probably would have had to known just about every one of these things. Okay. We also could. I guess we could have, if we were given a torque specification that we had to maintain. You know, we could solve for one of these things. You know, but you know, that's about it. Okay, so that's torque for you in a nutshell, and thank you for watching.